So in this video, what we're going to do is a derivation of a sort of general PDE for the case where we're moving beyond one dimension. So this really is a continuation of this sort of idea where we were thinking about, say, dye in a tube or heat in an iron bar, but now we're thinking more generally about some situation, trying to figure out what are the sort of local governing equations for how that physical quantity might change in time. So let's first just define a few sort of terms. Let's assume that we've got some physical quantity that we're interested in tracking over time and over space, right? So it's some function that depends on where I'm located and also depends on time. So this could be anything from sort of, a number of particles per meter cubed, right? So it could be a particle density, it could be an energy density, right? So for example, if I were thinking about how much thermal energy was stored in something, I would talk about how the thermal energy density was changing and was different in different places. It could be a charge density, it could be sort of any physical quantity as long as we're talking about something where the sort of idea of conservation makes sense. And the sort of thing that we're going to think about is some general, if we think about just some general region in space. So here's some region, and this region is, I'm going to say, some volume. Of course, I could do this in 2 dimensions as well, but we'll just think in 3 dimensions initially. So this is some volume V, and it's bounded by some surface S that sort of encloses that volume. So S is a closed surface that encloses the volume V. Now, if we wanted to ask the question, how much of that physical quantity is inside of that, this volume, we'd say, well, the amount of stuff inside would simply be a volume integral over that volume domain of whatever that function was. Right, so this would tell us the amount of stuff inside the volume at some time t. We're integrating over this volume, so this has units of number per meter cubed. This has units of meter cubed, so this tells me, say, how many particles are inside of this volume. So that's how we could figure out how much stuff is inside of it. If we wanted to ask how fast the stuff inside is changing, well, obviously we could take a time derivative of that. So the time derivative of that would tell us how fast the amount of stuff inside was changing. But if you think physically how stuff inside could be changing, there are a couple of ways that it could be changing. One way that it could actually be changing is if I've actually got stuff flowing out of this surface, right? So in fact, the rate of change of the stuff, total amount of stuff inside the surface, is related to what the flux is of stuff through the surface. So so one possible process is stuff leaving, and since flux is defined positively when it's flowing out, I would say that's minus the flux of stuff crossing the boundary S, right? And of course, another thing that could be happening is I could have some generation or destruction processes going inside, right? Maybe there's some chemical process that's creating more particles or that's creating more thermal energy inside. So I could also have some other terms here to represent sources or sinks. And I won't talk about those right now, so we're just going to pretend that we don't have that going on at this point. Okay? So, and you should sort of be able to look at this and say, this looks pretty familiar. This, the left-hand side looks like when I did this sort of tube example, right? The left-hand side is sort of how much stuff is inside of this chunk of tube. And the right-hand side, the negative of the total flux was basically, we thought about the flux going out minus the flux going in, which is the total amount of flux coming in. So there's a pretty close analogy here between this sort of 3-dimensional case and the 2-dimensional case. Well, to go a little bit further with this, we have to think a little bit about how we actually figure out what this flux is. And this flux is going to be calculated by thinking about what's the flux density of the material, or of the quantity, and then integrating that flux density across the surface. So let's take a second to just think about flux density. What is meant by that? Well, one thing to note about that is flux density is a vector quantity, right? It tells you the direction that the quantity that you actually have things moving, right? So if I think about having a flux density that's in that direction, what that says is if I'm watching in this way with some plane oriented like that, I see things crossing that boundary per unit time. If on the other hand I were watching, say, in a plane in this direction, I wouldn't see anything crossing this plane because the flux density would be parallel to that plane instead of normal to the plane. So flux density is a vector quantity, and the units of flux density is basically stuff per unit time per unit area if we're talking about a sort of three-dimensional volume enclosed by a two-dimensional surface. So if often we use the notation J vector to denote a flux density. So for example, in this case, if you were talking about number per meter cubed as being the quantity inside, your flux density would have units of number per second per meter squared, and it would basically be telling you in what direction and how quickly are particles moving into or out of this region. So then, having defined the flux density, we can finally calculate the flux. The flux is simply going to be the integral around that closed surface S of the flux density dot n hat dA. So we're doing a surface integral over this, right, and sort of asking the question for each little chunk of surface, how much stuff is coming out per unit time. The total amount of stuff coming out per unit time is the flux, and that flux tells me what the time rate of change of the amount of stuff inside of the surface is. So this is the first part of sort of thinking about how we come up with a partial differential equation for the generalized case. It's purely an integral formulation, and the integral formulation says the time rate of change of the stuff inside is equal to the negative of the flux coming out, right? And I'll stop here and make another video to now transition this to a differential case.